Hello students, in today's video we will learn about Newton's third law of motion and law of conservation of momentum. Newton's third law of motion describes the relationship between the forces that come into play when the two bodies interact with each other. In this figure, when the boy exerts a force on the wall exerts an equal force on the boy in the opposite direction. According to Newton's third law of motion, whenever one body exerts a force on another body, the second body exerts an equal and opposite force on the first body. In this case, the force exerted by the boy on the wall is known as action force, and the force exerted by the wall on the boy is known as reaction force. Action and reaction are two forces that act simultaneously on different bodies. Let's understand a simple experiment to prove that action force and reaction force are equal and opposite. As you can see, there are two spring balances A and B joined hook to hook. The other end of the spring balance A is attached to a hook which is fixed in a wall. If you pull the balance B, it exerts an action force of 1 Newton on the balance A. Then the balance A pulls the balance B with an equal and opposite force, that is reaction force, of 1 Newton. Since both the spring balances show the same reading of 1 Newton, we can say that the action force and reaction force are equal in magnitude. And since action force is acting towards east and reaction force is acting towards west, we can say that action forces and reaction forces are opposite in direction. Let's look at few everyday examples of Newton's third law of motion. When we walk on the ground, our foot exerts an action force on the ground, and the ground exerts a reaction force back on our foot. This reaction force exerted by the ground on our foot makes us walk forward. It is difficult for us to walk on ice because the friction is much less on ice or any slippery surface, and hence we cannot exert an action force on ice. Let us consider the case of a swimmer. A swimmer pushes the water backwards with his hands and feet to move forward in water. Then the pushed water exerts a reaction force back on the swimmer which pushes the swimmer forward. Although action and reaction forces are equal in magnitude, they do not produce equal acceleration in the two bodies. This is because the bodies on which the forces act have different masses. So, a body having less mass will experience more acceleration and a body of more mass will experience less acceleration because acceleration and mass are inversely proportional to each other. Let's understand this with an example. When a bullet is fired from a gun, the gun experiences a sudden backward movement or jerk. This backward movement is called recoil. Now let's understand, why does the gun recoil? That is, why does it move backward? When the gun is fired, it exerts an action force on the bullet. The bullet exerts an equal and opposite force on the gun. That is why the gun experiences a backward jerk. Now let's consider the acceleration experienced by both gun and the bullet. Since the gun has much greater mass, its acceleration will be less compared to the acceleration of the bullet. Now let's understand law of conservation of momentum with an example. In the figure, a car of mass m1 moving with a velocity v1 collides with a car of mass m2 moving with a velocity v2. After collision, the first car slows down to a velocity v1 dash and the second car speeds up to a velocity v2 dash. Here there is no loss of momentum in the collision. The momentum lost by the first car has been gained by the second car. Although the momentum of each car is changed, the total momentum, that is momentum before and after collision, remains same. Therefore, law of conservation of momentum states that when two or more bodies act on one another, their total momentum remains conserved provided no external forces are acting on the bodies. It can also be stated as momentum is neither created nor destroyed. Now let's mathematically express conservation of momentum for a given system. Suppose two balls of masses m1 and m2 are traveling with initial velocities u1 and u2. Let us assume that there are no external unbalanced forces acting on them. Let's consider the velocity of the first ball to be greater than the second ball. This is to let the collision happen. Let's say this collision lasts for time t. During collision, the first ball exerts an action force F12 on the second ball and the second ball exerts a reaction force F21 back on the first ball. Let V1 and V2 be the velocities of the first ball and the second ball after the collision. Now momentum of ball 1 before collision will be m1u1. Momentum of ball 2 before collision will be m2u2. Momentum of ball 1 after collision will be m1v1. Momentum of ball 2 after collision will be m2v2. From Newton's second law of motion, we know that rate of change of momentum is proportional to the net force. From this, we can write the rate of change of momentum of first ball is equal to the action force F12. So F12 is equal to m1 into v1 minus u1 by t. Similarly, the rate of change of momentum of second ball is equal to the reaction force F21. F21 is equal to m2 into v2 minus u2 by t. According to Newton's third law of motion, action forces and reaction forces are equal but opposite in the direction. So we can write F12 is equal to minus F21. Since both the forces are equal, we can equate the right hand sides of the two equations. If you equate, t will be cancelled. If you bring u1 and u2 on the left side and v1 and v2 on the right, we get m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. From this we can say that total momentum before and after collision is conserved unless an external force acts on the bodies. The device you see here is Newton's cradle. Newton's cradle aptly demonstrates law of conservation of momentum. When the first ball of the cradle collides with the second, the first ball stops, but its momentum isn't lost. It is just transferred to the second ball, then the third, then the fourth, until it reaches the very last ball. You witness this conservation of momentum as the last ball swings into the air with same momentum as the first ball. If the two balls are lifted into the air on one end of the device and released, then the two balls on the opposite end will swing in response. So that's it for today, students. In the next video, we will solve numericals on second law of motion and law of conservation of momentum. Thank you.